Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video, we're looking at refrigeration and liquefaction, Chapter 9, and in particular, we are looking at vapor compression refrigeration. So the basic vapor compression refrigeration cycle has us bring in a saturated liquid and vapor combination. We feed it into an evaporator where it is turned into a vapor, typically a saturated vapor. This gas is then compressed to a higher pressure, where it is then condensed, and to return it to its initial state, it all goes through a throttling valve. Now, in the condenser, we are going to have heat loss out of the system at a high temperature. And in the evaporator, we have heat transfer into the refrigerator from a cold temperature. And this would be, say, our food or the room of our house that we're trying to air condition. And this is often to the surroundings. There will be work required at the compressor, but our throttling valve, we assume, has Q and W both equal to 0, which means it is isenthalpic, or delta S equals, or delta H equals 0. Let's look at this example. A vapor compression refrigerator uses R12, often called Freon 12, as the working fluid. The pressures in the evaporator and condenser are 400 kilopascals and 1400 kilopascals, respectively. The refrigerant exits the evaporator with 3 degrees C of superheat. Now that's an odd one. We haven't really seen that one before. And it exits the condenser after being cooled to a saturated liquid. The compressor is 85% efficient, and based on this, we want to determine the coefficient of performance. So this given information, what they've told us is that the pressure at state 2 is 0.4 megapascals, and at state 4, it's 1.4 megapascals. I have a saturated liquid at state 4, but it is superheated at state 2 with 3 degrees C of superheat. Now what that means is that the temperature here is the saturation temperature plus 3 degrees C. Now what else do I know about this cycle to be able to get going? I know that the evaporator and the condenser are both at a pressure of 0.4 megapascals, and P3 would therefore be 1.4 megapascals. So those are isobaric processes. And I know that my throttling valve is isenthalpic, so H1 and H4 will be equal. And my ideal for my compressor is going to be constant entropy, so S2 and S3 for the ideal will be equal to each other. So if we go to data tables and begin looking this stuff up, then what I find, now we don't have these tables, so you're going to have to kind of take my word on it for some of this or go look in other sources. But at 1.4 megapascals at saturation, the temperature is 52.4 degrees C. The volume would be 0.000918. The enthalpy is 275.4, and the entropy is 1.249. This allows me to determine what H is for state 1. I also sort of have enough information to analyze state 2. What this is that the pressure is 0.4 megapascals and the temperature is 3 degrees higher than saturation. Well, I can look up the saturation temperature, and that will in fact be the temperature for state 1. It is 8.94 degrees C. If the pressure is 8.9 or 0.4 megapascals and the enthalpy is 275.4, then I can look this up, and it turns out it's a saturated mixture with 33% vapor, 67% liquid. But that also allows me to estimate the temperature of the state 2, because in that case, well, okay, it's not going to let me erase that. So this is add 3, so 11.94. And 11.94 and a pressure of 0.4, I can interpolate through the superheated tables and get 406.5 and an entropy of 1.732. What I know about the compressor says that the exit for the ideal compressor will have that same entropy. That entropy plus this pressure allows me to look up the ideal state 3, which is 59.3 degrees C. The volume is 0.01493 and 432.8. All right, so I now have enough data. I could look up more. I could calculate V's and S's for some of these other things. I don't really need them, so I'm not going to. But if I analyze my compressor, in the compressor, the ideal work is going to be H3 prime minus H2. 432.8 minus 406.5 is 26.3 kilojoules per kilogram. And therefore, the actual work for the compressor is the ideal divided by the process efficiency. So 26.3 divided by 0.85 tells me that 30.9 kilojoules per kilogram is the actual work. And this then allows me to estimate the actual enthalpy. Take state 2, 406.5, add the actual work, 30.9, and so state 3 will have 437.4 kilojoules per kilogram. So I've cleaned up our table. This is now the actual state 3. I haven't bothered with the V's and the S's. At this point, all I need is H values. And our work, our actual work for the compressor is 30.9 kilojoules per kilogram. If I want to find the heat transfer at the evaporator, which is the cold temperature, then I'm going to take H2 minus H1, which is 131.1 kilojoules per kilogram. At the hot temperature, this is the condenser, and that is H4 minus H3. Now that's the actual state 3, and that's negative 162 kilojoules per kilogram. And so the coefficient of performance for this cycle is 131.1 over 30.9, which is 4.24, which seems like a big number, right? We've been looking at power cycles, so it's a number greater than 1. We don't know how to evaluate that. So let's compare this to the Carnot efficiency for this temperature range. And so that is Tc over Th minus Tc, which is 8.94 plus 273.15. I need to work in Kelvin. But for the temperature Th minus Tc, that temperature difference, degrees Kelvin or degrees Rankine will not make any difference. When I subtract those two, I end up with 5.6. And so therefore I can compare 4.24 to 5.60. Yes, it's less than that. Seems like a good number based on the Carnot efficiency. So this concludes this example. What we're going to be doing in class next time is looking at how we make decisions about the refrigerant and the operating conditions that we use. Thank you very much for your time.